let's do some Newton's second law example problems. So our first example is a hockey puck moves over frictionless ice along an x-axis in one-dimensional motion. The puck's mass is m equals 2.2 kilograms. Forces F1 and F2 are directed along the axis and have magnitudes F1 equals 4 newtons to the right and F2 equals 2 newtons to the left. Force F3 is directed at an angle of 30 degrees downward and to the right and has a magnitude of 1 newton. What is the acceleration of the puck? So first and foremost, we have to draw a free body diagram. So we have the hockey puck, and then I know F1 is to the right, F2 is to the left, okay? And then it tells me that F3 is directed at an angle of 30 degrees downward. Now, usually that is an angle of 30 degrees to the horizontal, which means that is our angle right there. So since that force is at an angle, we know that we have to split that up into x and y components. Of course, the other forces acting on this hockey puck are the force of gravity and the normal force. But those aren't going to add to the net force in the horizontal direction because we know that this puck is accelerating in the horizontal direction, but I still draw them in my free body diagram. So first and foremost, let's break that force 3 vector down into x and y components. So force 3 is down and to the right. This angle right here is 30 degrees, and they also tell me force 3 is 1 newton. So my force 3x will be 1 newton times a cosine of 30. And then my force 3y will be 1 newton times a sine of 30. All right, so we get 1 times cosine 30 is 0.866 newtons. And then, of course, the sine of 30 is 0.5 newtons. And times 1. So that makes it easy. So now that we've split that up into x and y components, we can draw a new free body diagram. So the new free body diagram looks something like this. We have the force 1 to the right. I'm actually going to make some room here because I have my other component to the right as well. Force 1 is to the right. The x component of force 3 is also to the right. I have my force of gravity down. Y component of force 3 is also down because that was down and to the right. Force 2 is to the left, and then we have normal force up. Now, again, this puck is not accelerating up or down. So we're not really concerned about the vertical forces. However, when we get into friction next week and really what the force of friction entails, we will need those vertical forces, even if we're only moving in the horizontal direction. So you do still want to solve for that y component. Okay, so we know that we're accelerating in the horizontal direction, so we are concerned with those with those horizontal forces. So my net force in the x direction will be equal to mass times acceleration. Now I'm going to call right positive. It doesn't really matter which direction you call positive. I usually try to call the direction of acceleration positive, but I don't really know what direction the acceleration is right now. So if I get a negative number for my acceleration, I'll know that the acceleration is pointed in the negative direction, the other way. So net force, since I called right positive, that will be force 1, I drew that way too big, force 1 plus force 3x, and then I'm going to be subtracting force 2 because that is pointed in the negative direction, and then that equals mass times acceleration. So that's the net force. It's made up of all 3 of these forces right here, where these 2 are, let's do it in a green because that's like positive. These 2 are positive, and then this one right here is negative, okay? So continuing on, we have force 1. We know that that was 4 newtons. So we get 4 newtons plus force 3x, which was 0.866 newtons, minus force 2, which was 2 newtons, equals mass, which was 0.2 kilograms, times acceleration. So we get 4 plus 0.866 minus 2, and then we divide both sides by 0.2, and we get acceleration is equal to 14.33 meters per second squared. So that is our answer.